November 21, 1944. The rugged, mist-shrouded mountains of Kyushu, the southernmost of Japan's main islands, held a smoking secret. Rain mixed with sleet fell in relentless sheets, turning the red volcanic soil into a treacherous slurry of mud and ash. Major Saburo Horikoshi of the Imperial Japanese Army Air Service struggled to maintain his footing as he climbed the steep ravine, his breath visible in the frigid mountain air. He was not alone. A team of Japan's most elite aeronautical engineers, pulled urgently from the drafty design bureaus of Nakajima and Mitsubishi, scrambled alongside him. They were not there to rescue survivors. The violent impact of the crash hours earlier had precluded that possibility. They were there to perform an autopsy on a monster. Before them, emerging from the fog like the skeleton of a prehistoric beast, lay the twisted, charred remains of a Boeing B-29 superfortress. It was an alien object in this ancient landscape, a sprawling mass of duralumin and high-tensile steel that seemed impossibly large even in death. To the local farmers who had witnessed the fiery descent, it was a terrifying omen. To Major Horikoshi and the engineers, it was something far more dangerous. It was the physical manifestation of a nightmare they had long feared but never fully comprehended. This was not merely an enemy aircraft. It was a technological ultimatum delivered from the sky. The smell of the crash site was a complex, nauseating bouquet burning rubber, the acrid sting of high-octane aviation fuel, the metallic taste of vaporized magnesium, and the grim organic scent of death. But the engineers suppressed their human reactions, forcing themselves into the cold objectivity of scientists. They began to measure, they began to touch, and as they ran their gloved hands over the surviving sections of the fuselage, a collective silence descended upon the group, heavier than the low clouds pressing down on the peaks. The rivets were flush-headed, driven with a precision that suggested not human hands, but automated perfection. The skin of the aircraft was smooth, aerodynamic, designed to slip through the thin air of the stratosphere with minimal resistance. One of the senior metallurgists, a man who had spent 30 years studying the properties of aluminum alloys, stood before a massive section of the wing spar. He took a small file from his pocket and scraped the metal, then peered at the scratch through a jeweler's loupe. He stood there for a long time, rain dripping from the rim of his cap, before looking up at Major Horikoshi. His eyes did not hold anger or determination. They held the hollow, haunted look of a man who has just realized the foundation of his entire professional life has been rendered obsolete. The alloy was stronger, lighter, and cleaner than anything produced in the foundries of Tokyo or Osaka, and this was just the structural beam. The true terrors, they would soon discover, lay hidden inside the engines and the black boxes of the fire control systems. To understand the depth of the dread that permeated that mountainside in 1944, we must first journey back to the years preceding this moment, to understand the chasm that had opened between the combatants. The Pacific War, often remembered for its island-hopping campaigns and naval battles, was fundamentally a war of industrial capacity and engineering philosophy. Japan had entered the conflict with world-class aircraft like the Mitsubishi A6M0, a machine of exquisite agility and range. But the Zero was the product of a specific philosophy, lightness above all else. It was a samurai sword, sharp, fast, deadly, but brittle. It lacked armor. It lacked self-sealing fuel tanks. It was built by craftsmen who shaved ounces off the airframe by drilling holes in structural members, sacrificing survivability for performance. In stark contrast, the American philosophy was one of overwhelming power and redundancy, backed by an industrial base that operated on a scale incomprehensible to the pre-war Japanese economy. While Japanese artisans were hand-beating aluminum panels, American factories were pioneering mass production techniques that turned aircraft manufacturing into an automotive-style assembly line process. But the B-29 was not just another product of this system. It was the Manhattan Project of aviation. Its development cost of $3 billion exceeded that of the atomic bomb itself. It was the single most expensive weapons project of the Second World War, a gamble of unprecedented proportions by the United States Army Air Forces to create a weapon capable of striking the Japanese mainland from bases thousands of miles away. The engineers scrambling over the wreckage on Kyushu knew the rumors. They had heard reports of a super bomber, that could fly at altitudes where the air was so thin that human blood would boil without pressurization. They had heard of a plane that could fly faster than many of their own fighter aircraft, while carrying a bomb load that could level a city district. But rumors were abstract. The twisted metal before them was concrete reality. As the recovery teams began the arduous task of cutting the wreckage into transportable sections, the Japanese military hierarchy demanded answers. They wanted the technology. They ordered the engineers to reverse engineer the beast, to clone it, to turn the Americans' weapon against them. It was a command born of desperation, ignoring the fundamental reality that technology is not just a blueprint. It is the culmination of supply chains, metallurgy, chemical engineering, and manufacturing tolerances. The wreckage was transported to the aeronautical research facilities in the Kanto region, near Tokyo. Here, under the glare of harsh electric lights, the true autopsy began. The centerpiece of their investigation and the source of their deepest despair was the propulsion system. The B-29 was powered by 4 Wright R 3350 duplex Cyclone engines. These were 18-cylinder, air-cooled radial engines, massive power plants capable of generating 2,200 horsepower each. On paper, Japanese engineers understood the concept of a large radial engine. They had built their own 18-cylinder engines, such as the Nakajima Homare. But as they dismantled the captured R3000, 350 seconds, stripping away the layers of hoses and wiring, they encountered a level of complexity that defied their manufacturing capabilities. The heart of the B-29's high-altitude performance was not the engine block itself, but the breathing apparatus attached to it, the General Electric B-11 turbosupercharger. This device was the linchpin of the entire strategic bombing campaign. An internal combustion engine is essentially an air pump. It needs oxygen to burn fuel. As an aircraft climbs, the air density drops. At 30,000 feet, the altitude at which the B-29 was designed to cruise, the air pressure is roughly 1/3 of that at sea level. A standard engine would strangle, losing power until it could no longer sustain flight. The turbo supercharger solved this by taking the hot, high-pressure exhaust gases from the engine and using them to spin a turbine. This turbine was connected by a shaft to a compressor, which sucked in the thin outside air, compressed it to sea-level density, and fed it into the engine's intake. It sounded simple in theory. In practice, it was a metallurgical nightmare. The turbine wheel in the General Electric system had to spin at upward of 20,000 revolutions per minute, while being blasted by exhaust gases exceeding 1,500 degrees Fahrenheit. At these temperatures, steel glows cherry red and loses its structural integrity. It becomes soft, pliable, prone to a phenomenon known as creep, where the centrifugal force of the spinning turbine causes the blades to physically stretch and lengthen. If the blades stretched even a fraction of a millimeter, they would strike the casing, shattering the turbine and destroying the engine. The Japanese metallurgists analyzed the turbine blades from the crashed B-29 with growing horror. They discovered that the Americans were using a cobalt-chromium-tungsten alloy known as stellite, along with other superalloys like hastelloy. These materials required access to rare earth metals that Japan simply did not possess in sufficient quantities due to the effective Allied submarine blockade that had strangled their supply lines. But the shortage of raw materials was only half the problem. The other half was the fabrication technique. The American turbine blades were not forged or machined in traditional ways. They were precision, cast using the lost wax method, a technique traditionally used for jewelry and dentistry, now industrialized on a massive scale for war. When the Japanese engineers attempted to replicate these blades using their own available steel alloys, the results were catastrophic. In test bench trials, the domestic copies would deform and disintegrate within minutes of reaching operating temperature. The realization was absolute and crushing. They could duplicate the shape of the supercharger, they could copy the dimensions of the ducts, but they could not reproduce the material properties. Without the metallurgy, the design was useless. The B-29 could cruise comfortably at 32,000 feet, above the effective ceiling of most Japanese flak and fighter aircraft. The Japanese interceptors, struggling to reach that altitude, would be wallowing in the thin air, their engines gasping for oxygen, while the American bombers flew overhead, their engines force-fed by the turbochargers that Japan could not copy. But the engines were only the first blow. As the inspection teams moved to the fuselage, they encountered another technological barrier that seemed insurmountable: the cabin pressurization system. The B-29 was the first mass-produced bomber to feature pressurized crew compartments. This allowed the crew to work without bulky flight suits and oxygen masks, reducing fatigue on the long, grueling missions from the Marianas to Tokyo and back. To achieve this, the B-29's fuselage was built like a submarine, designed to hold pressure in rather than keep water out. The cylindrical sections were sealed with a level of precision that Japanese manufacturing tolerances could not match. When Japanese engineers examined the sealing compounds used around the windows and the joints of the B-29, they found synthetic rubber polymers that remained flexible at 60 degrees below zero, the temperature of the stratosphere. Japanese rubber, derived from natural sources in Southeast Asia, became brittle and cracked at those extreme temperatures. Even if they could build the pressure vessel, they couldn't seal it. A leak at 30,000 feet was not just an inconvenience, it was a lethal event. Explosive decompression could incapacitate a crew in seconds. The industrial gap here was not just about metal, it was about the chemical industry, the ability to synthesize materials that nature did not provide. The investigation moved from the engines and the airframe to the defensive systems, and here, the sense of technological inferiority shifted from despair to disbelief. The B-29 was defended by a central fire control system, a network of remotely operated turrets directed by analog computers. In a traditional bomber, like the B-17 or the Japanese G4M, Betty, the gunner sat behind the gun, looking through a sight and physically wrestling the weapon to track the target. The B-29 changed the paradigm. The gunners sat in comfortable, pressurized sighting blisters, manipulating small, precise optics. The General Electric computers, black boxes filled with gears, cams, and vacuum tubes, did the heavy lifting. They calculated the lead required to hit a moving fighter. They corrected for the speed of the bomber, the speed of the target, the density of the air, and even the gravitational drop of the bullet over distance. Most incredibly, they corrected for parallax error, the difference in perspective between the gunner's eye and the turret located varying distances away on the fuselage. A gunner in the nose could control the upper forward turret or hand off control to the side gunners. To the Japanese electronics experts, who were accustomed to simple optical sights and manual tracking, this was akin to witchcraft. They opened the casings of the fire control computers and found a dense thicket of wiring and potentiometers. The manufacturing precision required to mass-produce these analog computers was beyond the capability of the Japanese watch and instrument industry, which was already stretched to the breaking point. They realized that every B-29 was not just a bomber, it was a flying calculator, a robotic fortress that aimed its guns with mathematical certainty. The cumulative effect of these discoveries on the Japanese psyche cannot be overstated. It is one thing to lose a battle because the enemy has more soldiers or more courage. It is another thing entirely to realize that the enemy is fighting a different kind of war, utilizing physics and chemistry in ways you cannot comprehend or replicate. The report that eventually made its way up the chain of command to the Imperial General Headquarters was couched in the polite, evasive language of the time, but the core message was undeniable. The gap in industrial technology is too great to be bridged in the time remaining. Yet, the order to fight on remained. The engineers were told to do the impossible. They attempted to design high-altitude interceptors, aircraft like the Ki-87 and the Ki-94, which were designed to incorporate exhaust-driven turbosuperchargers. But the prototypes languished. The turbine blades failed. The pressurized cockpits leaked. The hydraulic systems seized. Every step forward in design was halted by a failure in materials science. The ghost of the B-29 hung over every drafting table in Tokyo. The human cost of this technological disparity was played out in the skies over Japan every day. Japanese pilots, flying unpressurized Zeros and Hayates, would scramble to intercept the incoming bomber streams. They would climb until their aircraft shuddered on the edge of a stall, their vision narrowing as hypoxia set in despite their oxygen masks. And looking up, thousands of feet above them, they would see the silver contrails of the B-29 seconds, marching in pristine formation, untouchable. The American crews, sitting in their pressurized, heated cabins, eating warm sandwiches and drinking coffee, were operating in a different environment entirely. One specific incident illustrates the tragedy of this realization. In the spring of 1945, a young engineer named Hideo Itokawa, who would later become famous as the father of the Japanese space program, was involved in the analysis of the B-29's targeting computer. He recalled holding one of the vacuum tubes from the system. It was a standard American component, available in any radio repair shop in New York or Chicago. But to Itokawa, the quality of the glass, the vacuum seal, and the filament spoke of an industrial consistency that Japan had never achieved. He realized then that the war was not being lost on the battlefield. It had been lost years earlier in the factories and the mines. The American capacity to produce millions of these high-quality components meant that their complex systems were reliable. Japanese complex systems, when they could be built at all, were temperamental prototypes. As the firebombing raids intensified, destroying the very industrial centers needed to build the countermeasures, the irony became bitter. The B-29 seconds were destroying the factories that were trying to copy the B-29 seconds. The technology was dismantling the capacity to replicate it. The city of Tokyo, with its wood and paper construction, burned under the rain of incendiaries dropped by the superfortresses. The engineers who had examined the crashed bomber in the mountains of Kyushu watched their own neighborhoods turn to ash, knowing exactly the mechanical marvels that were circling overhead, delivering the destruction with computerized precision. The futility was palpable. Attempts were made to copy the engine directly. The Mitsubishi Ha-211 was an attempt to create a high-power 18-cylinder engine, but it was plagued by vibration and cooling issues. It was never reliable enough for combat. The decision was made to strip down existing aircraft, removing armor and weapons to lighten them enough to reach the B-29's altitude. These special attack or ramming tactics were a reversion to the primitive, a desperate admission that technology had failed them, and only the sacrifice of flesh and blood remained. There is a profound melancholy in the archives of the Japanese aviation institutes from this period. The blueprints for their proposed superfortress killers are beautiful, elegant designs, drawn with the meticulous skill of master draftsmen. But they were fantasies. They assumed engines that didn't exist, fuel that couldn't be refined, and alloys that couldn't be forged. The B-29 stood as a monolith of reality against these paper dreams. It is also crucial to understand the logistics that supported the B-29, which the Japanese analysts deduced with sinking hearts. The B-29 was a thirsty beast. A single mission from the Marianas to Japan and back consumed thousands of gallons of high-octane fuel. The Americans had a fleet of hundreds of these bombers. The sheer volume of petroleum required to sustain this campaign was staggering. Japan, by 1945, was distilling fuel from pine roots in a desperate attempt to keep its few remaining interceptors flying. The B-29 wreckage told the story of a nation with limitless energy resources, while the examiners were shivering in unheated laboratories, their stomachs empty. The investigation of the captured B-29 seconds also revealed the American approach to user experience, a concept alien to the Japanese military ethos. The B-29 was designed to be flown by young men with limited training. The systems were automated to reduce pilot workload. The flight controls were boosted. The comfort of the crew was considered a factor in combat efficiency. Japanese aircraft were designed for the virtuoso, the samurai of the sky who could compensate for mechanical quirks with supreme skill. But there were no more virtuosos left. They had died at Midway, at Guadalcanal, at Leyte Gulf. The Americans had built a machine that allowed average pilots to dominate the battle space through superior engineering. This democratization of lethality was perhaps the most frightening revelation of all. As the war drew to its cataclysmic close in August 1945, the B-29 delivered the final, devastating blows that ended the conflict, the atomic bombs on Hiroshima and Nagasaki. It was the ultimate validation of the technology the Japanese engineers had stared at in confusion on that mountainside. The pressurized cabin, the heavy lift capacity, the long range, all of it was necessary to deliver the weapon that changed history. In the aftermath of the surrender, as American occupation forces swept into Japan, there was a strange meeting of minds. American technical intelligence teams sought out their Japanese counterparts. They wanted to know what the Japanese had learned. When the American officers met with men like Major Horikoshi and the team from the Nakajima laboratories, They found not defiance, but a sort of professional relief. The Japanese engineers were eager to ask questions. How did you solve the turbine cooling? What is the composition of the exhaust valve seat? How do you keep the spark plugs from fouling at that altitude? The answers they received confirmed their wartime deductions. The gap had been systemic. It wasn't that Japanese engineers were less brilliant. In many cases, their theoretical work was ahead of the Allies. It was that they lacked the deep industry, the network of suppliers, the quality control protocols, the raw materials, and the specialized tooling machines. This realization, born in the ashes of defeat, sowed the seeds for Japan's post-war resurrection. The engineers who had looked with envy at the B-29's flush rivets and reliable electronics did not vanish. They took off their military uniforms and put on the work clothes of the reconstruction. They took the lessons of the B-29, the importance of quality control, the necessity of precision manufacturing, the value of systems integration, and applied them to peace. The companies that had struggled to copy the B-29 engines, Mitsubishi, Fuji, the successor to Nakajima, Kawasaki, transitioned to building trains, ships, and eventually automobiles and electronics. There is a direct historical line that runs from the failed attempt to reverse engineer the General Electric turbosupercharger to the global dominance of the Japanese automotive industry in the 1970s and 80s. The obsession with total quality management, which became the hallmark of Japanese manufacturing, was in part a reaction to the trauma of 1945. Never again, they vowed, would they be beaten by superior manufacturing quality. The ghost of the B-29, the machine they couldn't copy, became the silent tutor of the Japanese economic miracle. Today, if you visit the Smithsonian National Air and Space Museum, you can see the Enola Gay, a B-29 superfortress, gleaming under the spotlights. It is a static display, silent and cold. But to understand its true significance, you must imagine it not as it is now, but as it appeared to those Japanese engineers in the mud of Kyushu in 1944. To them, it was not a museum piece. It was a terrifying glimpse into the future, a monolith that whispered a hard truth across the barrier of war. That courage alone cannot defeat the laws of physics, and that the destiny of nations is forged as much in the foundry as it is on the battlefield. The story of the Japanese engineers and the B-29 is more than a footnote in aviation history. It is a parable about the nature of technological progress. It reminds us that complex systems are fragile, that innovation requires a foundation of mundane industrial competence, and that the most terrifying weapon of war is often the one you cannot understand, let alone replicate. When those engineers laid down their calipers and looked at each other in the rain-swept mountains, they acknowledged a defeat that had nothing to do with ideology and everything to do with the brutal, unyielding reality of the material world. They had touched the future, and they had found it made of alloys they could not forge. To fully appreciate the magnitude of this industrial disconnect, one must delve deeper into the specific agony of the Japanese engine designers. The story of the Nakajima Homari engine serves as the perfect counterpoint to the Wright R3350. The Homare was a marvel of compact design, tightly wound, incredibly light, and pushing the absolute limits of what was physically possible with the materials at hand. It was a sprinter's engine, but the B-29's R3350 was a marathon runner, built with a robustness that seemed wasteful to Japanese eyes but was actually the secret to its strategic utility. When Japanese engineers stripped the cylinders of the captured Wright engines, they were struck by the machining patterns on the cylinder walls. This was the result of a process called honing, a finishing technique that created a crosshatch pattern of microscopic scratches. These scratches were not defects, they were oil retention reservoirs, ensuring that the piston rings remained lubricated even under the intense heat and pressure of long-duration flight. Japan had honing machines, but not of the consistency found in the American examples. The American cylinders were interchangeable. You could take a cylinder from an engine built in New Jersey and bolt it onto an engine built in Chicago, and it would fit perfectly. In Japan, engines were often hand-fitted, each one a unique individual that required specific maintenance. This lack of interchangeability was a logistical nightmare in the field, but seeing the American solution was a revelation of industrial discipline. The narrative of the B-29's fire control system also deserves a more granular examination, for it represents the dawn of the cybernetic age in warfare. The General Electric system used self-synchronous, motors. When a gunner in the sighting blister moved his sight, an electrical signal was sent to the turret, where a matching motor would move the guns to the exact same position. This fly-by-wire predecessor required electrical components of immense stability. The Japanese electrical industry, hampered by a lack of high-quality mica for insulation and shellac for coating, struggled to produce servos that didn't drift or short out in the humid jungle conditions of the Pacific. Imagine the scene in a laboratory at the Tokyo Imperial University, where a team of electrical engineers has connected a captured GE computer to a power source. They move the input dial, and the output shaft rotates with eerie smoothness, stopping instantly when the input stops. There is no backlash, there is no jitter. It is damped, precise, and immediate. The professor leading the team looks at his students, young men who should be designing the power grid for a post-war Japan, but are instead trying to understand a weapon of mass destruction. He explains that the calculations happening inside this box, differential calculus performed by rotating gears, would take a human mathematician minutes to solve on paper. The box does it in milliseconds. The realization is not just about the war, it is about the obsolescence of the human mind in the loop of destruction. We must also consider the B-29's role as a catalyst for the Japanese radar development, or rather, the failure thereof. The B-29 seconds often flew at night, using their own radar, the AN divided by APQ-13, to navigate and bomb through the cloud layers. The Japanese captured examples of this radar from downed aircraft. They saw the magnetrons, the vacuum tubes that generated the microwave pulses. Japan had actually invented the cavity magnetron years earlier. The Yagi-Uda antenna was a Japanese invention, but the military and naval rivalry had prevented the technology from being effectively integrated. Seeing the American implementation, compact and ruggedized for flight, was a bitter lesson in inter-service cooperation and systems integration. The Americans had taken a Japanese theoretical concept and weaponized it against them, mass-producing it with a fidelity Japan could not match. Let us return to the human element, to the pilots who had to face this technological juggernaut. There are accounts from Japanese Army Air Force pilots describing their encounters with the B-29. One such pilot, flying a Kawasaki Ki-45 Toryu, described the B-29 as a porcupine of fire. When he attempted to attack from the rear, the standard blind spot for bombers, he was met by the radar-directed tail turret. The 20mm cannon in the tail of the B-29 could snipe him from a kilometer away. He described the sensation of flying into a wall of lead that seemed to be aiming itself. The psychological impact of facing a weapon that didn't seem to miss was devastating to morale. It eroded the samurai spirit, replacing it with a fatalistic acceptance of the technological superiority of the enemy. The investigation of the B-29 also revealed the American mastery of logistics and supply chains, evidenced by the packaged nature of the components. The engines were designed as power eggs, complete units with cowlings, oil coolers, and mounts that could be swapped out in the field in a matter of hours. A Japanese engine change was a multi-day affair, involving complex realignment. The Americans treated the B-29 not as a precious artifact, but as a consumable industrial product. If an engine failed, you didn't fix it. You threw it away and bolted on a new one. This disposable mentality was shocking to a resource-starved nation where every screw and bolt was hoarded. It spoke of a wealth so vast it was incomprehensible. The fuel that powered these engines was another point of despair. The B-29 seconds ran on 100 over 130 octane aviation gasoline, a rich, volatile brew that allowed for high compression ratios and massive power. Japan, cut off from the Dutch East Indies oil fields by US submarines, was running its aircraft on 87 or 91 octane fuel, often adulterated with alcohol or pine oil. This poor quality fuel caused knocking and pre-ignition, destroying engines from the inside out. When Japanese chemists analyzed the fuel residue in the tanks of the crashed B-29 seconds, they found lead additives and alkylates that were the product of advanced refining capabilities Japan did not possess. The very fluid coursing through the veins of the American bomber was chemically superior. In the frantic final months of the war, the Japanese government launched the Project Z initiative, a final, desperate attempt to build an intercontinental bomber, the Nakajima G-10N Fugaku. It was to be larger than the B-29, with 6 engines and the range to bomb the continental United States. But as the engineers worked on the design, the lessons of the B-29 crash investigation haunted them. To build the Fugaku, they would need the very metallurgy they had failed to replicate. They would need the spark plugs, the tires, the hydraulic fluids. The Fugaku remained a paper airplane, a fantasy of lines and numbers that never left the drawing board. It serves today as a symbol of the disconnect between ambition and capability. The story extends to the structural integrity of the airframe itself. The B-29 used large, flush-riveted panels to reduce drag. The Japanese manufacturing standard relied on smaller panels, which meant more joints, more rivets, and more weight. When the Japanese engineers calculated the drag coefficient of the B-29 based on the wreckage, they found it was remarkably low for such a large aircraft. The smooth finish was not just for aesthetics, it was a range, extender. Every ounce of drag reduction meant fewer gallons of fuel burned, which meant more bombs carried. The American obsession with aerodynamic cleanliness was a form of efficiency that the Japanese, with their ragged, paint-peeling late-war aircraft, could only envy. There is a cruel irony in the fact that the B-29, the destroyer of Japanese cities, was also the vessel that carried the seeds of Japan's rebirth. After the surrender, the occupation forces brought in jeeps, trucks, and aircraft that needed maintenance. Japanese mechanics, hungry and looking for work, were hired to service these machines. As they took apart American transmissions and differentials, they learned the standards of SAE, Society of Automotive Engineers. They learned about tolerances, about standardized parts, about the robustness of design. This hands-on education was the transfer of technology that the wartime engineers had failed to achieve. The reverse engineering finally succeeded not in the service of war, but in the service of peace. The narrative of the B-29 examination is also a story about the blindness of insular societies. Japan had convinced itself that spirit, Yamato Damashi, could overcome material deficiencies. The B-29 was the hard, cold proof that spirit cannot replace a turbosupercharger. It was a physical rebuke to the metaphysical doctrine of the Japanese military. The engineers were the first to see this because they spoke the universal language of physics. They knew that gravity, thermodynamics, and aerodynamics do not care about the emperor or the Bushido code. They care only about mass, energy, and velocity. In the wreckage of the B-29, the engineers saw the triumph of materialism over mysticism. Let us zoom in on one specific component that baffled the examiners: the Norden bombsight. While the B-29 relied heavily on radar, the optical bombsight was still a marvel of analog computing. It used a gyroscope to stabilize the view, allowing the bombardier to keep the crosshairs on the target even as the plane buffeted through turbulence. The Japanese had gyroscopes, of course, used in their torpedoes, but the miniaturization and precision of the Norden sight were on a different level. The bearings in the gyroscope were so smooth, they were almost frictionless. Japan's ball-bearing factories had been primary targets for the very bombers that carried these sights. The destruction of the bearing industry meant that domestic gyroscopes became increasingly erratic, while the American sights remained deadly accurate. It was a vicious cycle. The accurate sights allowed the destruction of the factories needed to build accurate sights. The emotional toll on the Japanese engineers led to a peculiar phenomenon known as victory disease, in reverse. In the early war, they had underestimated the Americans. Now, staring at the B-29, they risked overestimating them, seeing them as omnipotent gods of technology. This fatalism spread from the technical corps to the general staff. If the Americans could build this, what else could they build? The atomic bomb was the answer to that unspoken question, but even before Hiroshima, the B-29 had already proven that the war was unwinnable. Consider the specific alloy, 75 seconds, an aluminum-zinc-magnesium alloy, used in the upper wing skins of the B-29. It offered a strength-to-weight ratio that was significantly higher than the duralumin used in the Zero. The Japanese metallurgists identified the zinc content, but couldn't master the heat treatment process required to prevent the alloy from becoming brittle and susceptible to stress corrosion cracking. They tried. They melted down pots of experimental mixtures, altering the cooling times, quenching in oil, in water, in air. But the plates cracked. They warped. The secret wasn't just the recipe, it was the cooking technique, the precise temperature control of the giant industrial ovens in American factories, ovens that were controlled by thermostats more accurate than anything in Japan. The investigation also touched on the mundane, the crew survival gear. Inside the captured B-29 seconds, the Japanese found inflatable life rafts, emergency rations, signaling mirrors, and first aid kits containing sulfur drugs and morphine syrettes. The quality of the rubber in the life rafts was better than the tires on Japanese trucks. The rations were sealed in foil and cellophane, waterproof and preserved. To a Japanese soldier, who was often expected to fight on a handful of rice and die for the emperor, the fact that the enemy spent so much money and engineering effort just to keep a downed crew alive was a cultural shock. It spoke of a society that valued the individual soldier, or at least the investment in his training, in a way that Imperial Japan did not. The B-29 was, in essence, a flying ecosystem. It carried its own atmosphere, its own electricity, its own defense, and its own life support. It was a spaceship before the age of spaceflight. For the Japanese engineers, men who were used to the open cockpits and canvas-covered control surfaces of the 1,930 seconds, the B-29 was a leap across a generational divide. They were trying to bridge the gap from the age of biplanes to the jet age in a single jump, while their cities burned around them. As we approach the conclusion of this analysis, we must recognize the legacy of those desperate examinations. The blueprints drawn from the crashed B-29 seconds did not produce a Japanese superfortress. They produced something else, a generation of engineers who understood deeply, viscerally, the importance of materials, science, and production engineering. Men like Soichiro Honda and Masaru Ibuka, co-founder of Sony, lived through this era. They saw the consequences of inferior technology. They vowed to build products that were not just good enough, but superior to the American originals. The B-29, therefore, occupies a unique space in history. It was the instrument of Japan's destruction, but also the template for its reconstruction. It destroyed the old feudal Japan, burning down the wooden cities and the rigid hierarchies, and in the cleared ash, it laid the foundation for a modern, technocratic state. The B-29 shock was the catalyst that transformed Made in Japan from a label of cheap inferiority to a badge of global excellence. In the final assessment, the story of the Japanese engineers and the B-29 is a tragedy in the classical sense. It is the story of brilliant men trapped by the limitations of their circumstances, striving against an inevitable fate. They measured the wingspan of the giant, they weighed its heart, and they found themselves wanting. But in that honest, brutal assessment lay the seeds of their future redemption. The B-29 did not just defeat Japan, it taught Japan how to win the peace.